Alright, so let's jump into some examples. I'm going to go through these things here to help you with not only the 10.1 practice A, but will also help for your distance learning assignment that you need to submit on big ideas today. One thing I do want to, I missed something over here. When I said concentric circles, it's important to know that concentric circles, they share a common center, right? So the center of the smaller circle is the same as the center of the bigger circle. Okay, all right, so let's jump into some examples here. So name two radii. So remember, a radius is a segment who has an endpoint on the center and an endpoint on the circle itself. So I can see that clearly AB, that would be a radius. And I'm going to use my segment right as a segment by putting a line over the two letters. And then another one here, I can see, well, A also could extend to D, and this segment AD would be another radius. There is a third one shown on here. You could also write AF. Alright, so let's take a look at what chords do we have on here. Well, remember, a chord, the endpoint of the segment they both need to be on the circle. So your chord here is going to be CE. You also have another chord that is DF, but that is what we're going to go into number 3. The diameter. Remember, a diameter is a chord, but it goes through the center. In other words, it contains the center. So your diameter here is going to be DF. Now, a secant. Well, we're looking for a line that intersects the circle at 2 points. We clearly have a line here intersecting at D and E. So our secant is going to be DE. And I draw that little line over the top of it. Name a tangent. Well, tangent, we have this line here. Looks like it only has one point of intersection, which is a tangent line. That point of tangency. So I don't have two letters that are on this line, so I just have to use the word line and then one point that is contained in the line. So I'm going to call this line B. And actually the point of tangency is B there. Alright, so that is doing a set of problems for vocabulary. And let's continue here. So tell how many common tangents the circles have and draw them. Alright, well, remember, a tangent line can only hit the circle at one point. I can see like there's probably going to be some sort of tangent line that hits both of these circles up there somewhere. And even if I try to draw, I'm going to change colors here. If I draw any other line of tangency around this circle, none of them are going to also be shared with the other circle, except for, it looks like one. It's going to be probably touching here and go through there. And that looks to be it. Now we go to number 8. Are these internal or external? Well, remember, in the notes we had this idea of this segment that connects the centers. Now, do either one of these tangent lines intersect that segment that connects the centers? No. So we know that both tangent lines for this diagram are external. Okay, let's go to, I'm going to try to move quickly here. I want to keep this video under 10 minutes. So we're already about 4.5. Alright, so find BD. Well, BD is this segment here. How am I going to find it? Well, one thing that I didn't get to in your vocabulary is that a point of tangency, which is here, it is always, and that tangent line is always perpendicular to a radius. In other words, there's always going to be a 90-degree angle from a radius to a tangent line anywhere on that circle. So you're seeing we're creating a right triangle. So again, any tangent line creates a right triangle, essentially, in a circle. So those of you who thought that triangles were going away, sorry, they're not going anywhere. So let's now use this to figure out what this segment would be. Well, you can see that we have two legs and a hypotenuse, and anytime we need to find one of those sides, we can use the Pythagorean theorem. So in this case, we're going to use our a squared plus b squared equals c squared. Let's plug in our numbers here. So I'm going to have 5.5 squared plus this unknown we don't know, BD, but we'd square that, and we have to set that equal to the hypotenuse, which in this case is just 10 squared. Alright, so let's calculate some of this. One thing I want to show you is, I know Mr. Kluznik had a different calculator that he used. I'm going to show you another resource if you like this one too. I like to use Desmos. So Desmos has a scientific calculator set up. Follow the link here. But we want to get some numbers here. So I'm going to do 5.5. That's the square button here. I'm going to see it's 30.25. So let's jump back to my notes here. So I have 30.25 plus whatever this segment is, BD squared. We don't know what it is yet. And then 10, which is 100. Well, I'm running out of space here. I'm going to bring this up here. BD squared is going to equal 100 minus 30.25. So that's going to bring us to 69.75. And we're just going to need to take the square root of both sides to find that BD. Again, I'm going to jump to my Desmos calculator. So I had that 100, and I subtracted out that 30.25, and I got the 69.75. So now I want to take the square root. I'm going to clear this first, excuse me. Let's take the square root of 69.75, and I'm going to get 8.35. And let's jump back and see what the question asks. It doesn't specify if it wants it to the nearest tenth or hundredth. Let's just do the nearest tenth for now. So that's going to be 8.4, let's say. Okay, so that is BD. Now, point C is also a point of tangency. So now we're moving on to number 10 here. So C over here is also a point of tangency. So you got to imagine that there's another line that connects this, creates another right triangle here. So if BC equals 4x plus 6, so this segment here is going to be this 4x plus 6. Find the value of x to the nearest tenth. Well, what we've actually created here, if you look at this, this is a radius over here, so this needs to be 5.5. What we have is a congruence theorem from your triangles. We have HL, we have hypotenuse leg. They both share 10, the same hypotenuse, and they have a leg here. In that case, we know that all of their sides are congruent and all of their angles are congruent. So this BC actually equals BD. So by HL, we know that these two triangles are congruent, and we know that this segment BC is going to equal BD. So remember, we just found BD. BD was 8.4, and we were given BC as an expression of 4x plus 6. We'll do a little algebra here. We're going to subtract 6 from both sides to get 2.4, and then we're going to divide 4 both sides. Jumping back to Desmos. 2.4, we're dividing that by 4, we're going to get 6/10 or 0.6. You can kind of see that too. This is really just 24 divided by 4, which is 6, and then you'd have to move the decimal over. So wouldn't necessarily even need a calculator for that one. Alright, so remember, when you have two tangent lines and they meet at a common point, those tangent segments from the point of tangency to the common point are going to be congruent. And we're going to actually use that in the next set of videos here.